should say at the outset, Kurt Gödel's perhaps not as famous as many of the big thinkers who I think Gödel belongs in this sort of company, such as Darwin, Newton, Einstein, Aristotle and the like. Main reason, I think, is logicians and mathematicians don't get their due. I think, they don't it's hard to understand what a mathematician does. You can explain to people what was the basic ideas of Darwin or the basic ideas of even Newton. Einstein's a little bit harder, perhaps, but since we have many very good popular science writers who tend to particularly focus on physics, a lot of people have at least a good idea of what basics of some of Einstein's work and Newton's work. But mathematicians, I think, get the rough end of the stick sometimes. And Kurt Gödel certainly belongs in that sort of company. I think the idea of the incompleteness theorem, which is what I really want to focus on tonight, is one of the truly revolutionary ideas of modern thought. Absolutely monumental result. One of the major results in logic. Many people have said Kurt Gödel is right up there with Aristotle, and that the incompleteness results were the first major results in logic since Aristotle. So this is really big stuff. It will involve a little bit of logic and mathematics, but I will tread very gently through the technical details. In fact, why I chose Gödel, apart from anything else, is that the idea itself is very simple. The incompleteness theorem that we'll get to shortly is a very intuitive and simple idea, intuitive after the fact, but groundbreaking. So here is Kurt. A quick biography. Born in 1906 in the city of Brunn, now in the Czech Republic. Graduated in 1924, studied physics, mathematics and philosophy at the University of Vienna. Graduated with a D.Phil in mathematics in 1929 with a spectacular thesis, which I won't talk about tonight, and continued his work there at the University of Vienna until his departure for the US in 1940. Then he took up a position with a good friend. He'd visited the US a couple of times prior to that and had met Albert Einstein, was very good friends with Einstein, and he ended up at the Princeton Institute for Advanced Study, and regular walks, had his daily routine of going for walks and chats with Einstein. And he remained there until his retirement in 1976 and died a couple of years later from starvation and exhaustion. You might think a sad end to such a great life, but if you're a rock star, you aspire to sort of die in a plane crash like Lynyrd Skynyrd or Buddy Holly or Otis Redding, or second best, drown in your own vomit like Jimi Hendrix. But that's kind of, if you're a rock star, that's what you're after. If you're a mathematician and a logician, dying of starvation and exhaustion is right up there with drowning in your own vomit. You might think that being a mathematician and a logician, the personality disorder was redundant, but that would be a little bit mean-spirited. So some of his achievements, 1929, his doctoral dissertation on the completeness of first-order logic. I won't explain what this means, but that was a major result at the time, at the age of 23. The results will mostly focus on the first and second incompleteness theorems at the age of 25. Then did some groundbreaking work in set theory, which had actually been carried on through most of his career, but perhaps the most famous of these results was a result in 1940. And if we get time, I might just mention these novel solutions to Einstein's field equations, just because they're so quirky and give you sort of some insight into the diversity of things that Kurt Gödel carried around in his head. He was a foremost logician and mathematician, but he actually made major contributions to general relativity as well, in the most quirky and sort of odd way. So I hope we'll have time to just say a little bit about those solutions to Einstein's field equation. So Like any big thinker, you've got to understand a little bit about the times that they were thinking, and no exception here. And Kurt Gödel came along at a fascinating time for mathematics and logic. In the early 20th century, the foundations of mathematics were in crisis. It's hard to overstate how serious things were in mathematics at the time. Bertrand Russell had shown that set theory was inconsistent. Set theory being the foundation, or at least that was the hope for everyone, that set theory was the mathematical theory that would underpin all of the rest of mathematics. This truly rigorous axiomatic system was the great hope of mathematics. And Bertrand Russell showed that it was inconsistent. It's not just has a bit of a flaw or a bit of a blemish, that's about as bad as it gets for a mathematician. On the other side of things, Cantor had proved that if we have one infinite set, such as the natural numbers, the counting numbers, 1, 2, 3, 4, 5, 6, and so on, there are infinitely many of them. If we have one infinite set, and surely we do, because at least we have the natural numbers, there are infinitely many infinite sets, all that can be ranked in order. So it's not just a whole bunch of infinite sets all have the same size, but there are infinitely many different infinities. Hard to wrap your head around what that means without going into the mathematics. But this had been shown to be a natural consequence of the standard set theory of the time, along with the assumption that there is an infinite set. Again, amazing results. But both worrying in their particular ways. On the one hand, that mathematics is inconsistent. Just to get a sense of, who cares? Mathematics is inconsistent. Well, given that it's inconsistent, and given the classical logic that we are supposed to be using here, you can prove that 2 + 2 = 5. You can prove that I'm Elvis Presley. You can prove anything you like. The Riemann hypothesis, one of the most outstanding results in mathematics, can be proven in 5 lines, given that you've got an inconsistent theory. So it's really bad. You can prove all sorts of things which are true, but all sorts of things that are not true either. In fact, you can prove every other contradiction as well. One contradiction and it blows up. That's worrying for obvious reasons. The infinite stuff, worrying for more subtle reasons. Just was not clear that people really had a good grip on what infinity was, that there could be infinitely many different infinities. If one infinity is bigger than the first infinity, then surely the first one wasn't really infinite. There must be something bigger than it. It can't be infinite. So people were worried that they even had a good grip on what infinitely many objects of any kind meant. And people were trying to find a consistent set theory, and at the same time many of them were wary of Cantor's work on infinity. So along comes Frege, and he tried to set things on a firm basis. He thought, well, no wonder we don't understand all this business about infinity. We don't even understand the number 2. What on earth is the number 2? What's the number 3? What are the natural numbers about? What are they? We know how to use them and we know how to say things like 2 + 2 = 4, but what are they? And he worried about this, and most other people thought he was just mad. Of course we know what the number 2 is. What the hell are you talking about? But he really worried, and he thought that this was the root of a great deal of the problems in mathematics, that people didn't have a firm understanding of what mathematics was about. So he set things on a very firm foundation, laid out the assumptions, axiomatized basic arithmetic, and as often happens, once you make it very clear what's going on, problems jump out at you. And this is what happened to Frege. Bertrand Russell, who was very influenced by Frege's work and had been reading Frege, realised that there was an inconsistency in Frege's system. And he wrote this very nice letter to Frege a matter of days before his monumental work went to press, saying, Dear Professor Frege, if I may be so bold as to suggest that there's an inconsistency in your theory. And Frege, for what he, to great credit to Frege, he saw it immediately and realised that this was devastating. What he didn't realise, actually, was this problem is generalisable. It wasn't just a problem for Frege, it was a problem for mathematics at the time. So to get a grip on what this contradiction is, a very, very old philosophical puzzle called the liar paradox, which is just simply this sentence is false. Now, if I think about that sentence for a moment, two possibilities. Either it's true or it's false, right? So if it's true, then what it says is the case. And what it says is that it's false. So if it's true, it's false. That's bad, right? Must be false. But if it's false, well, that's what it says it is. It says that it's false. So if it's false, then it's true. So if it's true, it's false, and if it's false, it's true. Contradiction. Well, contradiction on the assumption that it takes a truth value at all, but why shouldn't it? It looks like a perfectly well-formed sentence of English. And philosophers, you might think, we don't have a lot to do, and we worry about things like this disproportionately, Philosophers have worried about this for a couple of thousand years. And to be quite honest, we're no closer to a solution than we were 2,000 years. But we've had a lot of fun in the meantime. Russell saw that this problem was generalisable to mathematics as well. So I won't go into the details, but the idea is very simple. You just consider a set. So a set is just a collection of things. The set of natural numbers, the set of people in this room, the set of chairs in this room. These are all sets, collections of things. You can have sets of sets. So Russell said, okay, what about the set of sets that are not members of themselves? And if you've done a little bit of mathematics or logic, you'll see that this is just the liar sentence in set theory form. Okay, so once you form this set, then you just ask the question, okay, is that set a member of itself or is it not? If it is, then it's not, and if it's not, then it is. You get exactly the same conundrum as you do with the liar paradox. So the Russell set can be proven to be both a member of itself and not a member of itself. That's bad. Mathematics is not supposed to license those sorts of things. This is when Russell announced his result to Frege. It was a problem for Frege, but it was also a problem for just general set theory. In a way, Frege had just made the problem so transparent because he'd been so clear about his assumptions. Now, shifting to the infinities and Cantor's work, just to get a flavour for this, it's not that important, but it is kind of, well, I'll admit to it, I'm a nerd and I love this kind of stuff, so I'll just share with you some of the delight in set theory. So here's what Cantor was mucking around with. An important operation on sets is the power set. So the power set, once you've got a set of things, say I've got the set of people in this room, I can then think of the power set of that, which is the set of all subsets. So it's the set that consists of me, then there's the set that consists of Meredith, and there's the set that consists of the gentleman here in the front row, then there's the set that consists of Meredith and me, and all the combinations, okay? All the ways you can pack that up, that's the set of all subsets. That's called the power set of a set. And according to set theory, you can always form the power set. If you've got a set, you can have a power set of it. No problems. So here's an example. Take the set that consists of just two things, 0 and 1. So the set those curly brackets, the first little curly brackets here, just mean that's the set. 0 and 1 considered as an object together, one thing. The collection of 0 and 1 together, that set has two things in it, 0 and 1. The power set of that has, well, the empty set is always a subset of a given set. It's got the set that contains just the 0, just the 1, and 0 and 1. So the power set has got four things in it. 1, 2, 3, 4. Okay. Cardinality. Cardinality of a set is in some sense the size of the set, how big the set is, how many elements in it, if you like. So if two sets have the same cardinality, if and only if the elements of one can be put in one-to-one correspondence with the other. Okay, so what that means, this is actually a crucial insight of Cantor, was that you don't have to count the things. You can just see if you can put them in one-to-one correspondence. So for instance, I don't have to do any counting at all to know that there are more chairs, there are more seats in this room than there are people. Why? Well, I just note that every person is paired off with a seat and there are some left over. So the cardinality of the set of chairs is greater than the cardinality of the set of people, to put it in a nerdy set theory talk, right? But I don't have to sort of count the chairs, then count the people, and note that the number of chairs is greater than the number of people. I can just do the one-to-one correspondence. And what's interesting about this will work for infinite sets. You don't have to actually count them as long as you can pair them off. So, just to get a feel for how this connects up with the power set stuff, remember the cardinality, we write these little lines here. Those of you who don't like symbols, don't worry about this too much. This is just me showing my nerdy streak. But the basic idea is quite simple, that the size of the power set is the size of this thing, which is 1, 2, 3, 4, we already established. So the cardinality of the power set here is 4 from our previous example. The set that we started with, the set that contained just 0 and 1, the cardinality of that is 2. And interesting that the cardinality of the power set is 2 to the 2, which is greater than 2. Okay, that turns out to be a very, very deep and generalisable result. Which brings us to Cantor's theorem. He showed that if you've got some set and the cardinality of the set, so if you've got some set, certain size, that's all it means, you've got some size kappa for the set, then the power set will be 2 to the kappa. And, here's the kicker, 2 to the kappa is always greater than kappa. Okay, so what does that mean? It means if you've got a set and you form the power set of it, then the size of the second set, the power set, will always be bigger than the first. Okay, we just saw that in that one little example. Not so startling, you might think. Think about this case. What if the first set is infinite? Form the power set of the natural numbers, 1, 2, 3, 4, 5, 6, 7, 8 to infinity. There's infinitely many of them. The power set of the natural numbers is infinite, but it's a bigger infinity than the natural numbers. Right? Do it again. Take the power set of that. Another infinity, bigger than either of the previous two, and so on and so forth. Power set operation is always licensed in mathematics. You can always take power sets of any set. If you've got one infinite set, you've got infinitely many of them, and they're stretching out infinitely many sets larger and larger than each other. And this leads to all sorts of strange puzzles. I won't go into them, but people were really worried about this. The whole idea of infinitely many infinities is all, if that's not sort of disturbing you enough already, all sorts of, puzzles you can get. How many natural numbers are there? Okay, let's call, for argument's sake, let's call that number Aleph 0, as mathematicians do. How many even natural numbers? Every second one, 2, 4, 6, 8. Clearly there's less of them, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to infinity. Now only every second one, you're leaving out half of them. 2, 4, 6, 8, right? How many of them are there? Aleph 0 again, the same number. They're both infinite sets, but that's not what makes one set larger than another, is not even leaving out half of them, for instance. There's something else. It's the power set operation that does this. So this cute little trick that I think it goes back to Hilbert. Imagine you've got an infinite hotel, infinite number of rooms in it, and it's full. Business is good, right? If you're a hotel owner, it doesn't get any better than that. Infinite number of rooms, and the rugby league grand final is on, so everybody's there. It's full. Someone else knocks on the door and says, "I'd really like a room." First temptation is to say, "Sorry, we can't fit you in. We're full." But then the owner says, no, we can. I'll move the person in room 1 into room 2, the person in room 2 into room 3, the person in room 3 into room 4, and so on. Now room 1's vacant. We've got a room. You can do that. That's one of the results, the sort of odd results you get with infinity. You can always make room for another. So, this is the background. Here are sort of the worries that were permeating the mathematical culture of the time. Various responses, one of which most famously by one of the all-time greatest mathematicians, David Hilbert. Hilbert had this program to set mathematics straight because everybody was worried. So what he thought was that the infinite stuff, unlike some people who wanted to chuck it out, that crazy stuff about infinitely many infinities, let's try and restrict mathematics to more sensible things. Finitism, for instance, was a view. You can have only finite sets, but for every finite set there will be a bigger finite set, but no infinities, no completed infinities, if you like. Hilbert didn't like that. He thought he loved what Cantor had done. He'd loved the infinite mathematics. It was truly beautiful, one of the greatest creations of human thought. He didn't want to lose that. So he thought, what we'll do is, we've got a good enough grip, modulo a few twists and turns, but we don't need to go into that. We've got a good enough grip on the finite mathematics, so what we want to do is sit the infinite stuff on top of it, but treat it quite differently. The infinite stuff will be just kind of this formal game. When you've got a symbol like that, you can replace it with a symbol like that. That's just a rule of mathematics. So we treat it like you do with the rules of chess, for instance. What is a rook in chess? Well, it's nothing other than the thing that plays the role of the rook. It's governed by certain rules. It doesn't matter whether it's made of wood, made of paper, made of porcelain, whatever. A rook is just that thing that plays the rook role. Hilbert thought mathematics is a game just like chess. There are manipulations you're allowed to make, and that's what keeps it on the straight and narrow. All we need to do then, mathematics is a kind of logical consequences. That's all you're doing, fleshing out logical consequences, which prompted Bertrand Russell to say mathematics may be defined as a subject in which we never know what we're talking about nor what we're saying is true, because you're just manipulating symbols, you're playing this formal game. He wanted to preserve the rich, infinite character of mathematics. As I said, he wasn't going to get rid of any of it. He'd need to make a story about how the infinite stuff fitted in, and he thought of it as a formal game akin to chess. Famously, Hilbert said, "No one shall expel us from the paradise that Cantor has created for us." He would not have any truck with the idea that we sort of restrict mathematics. We want as much of it as we can. This is, Hilbert's respect for the whole of mathematics. But to do this, and here's where we get back to Gödel, to do this, Hilbert required to prove that mathematics was consistent. And also that it was complete, that you can do everything by this method. If you treat it as a formal game, that you want to be able to crank out the theorems by playing this formal game. That's all you do. You have no other access to truths of mathematics except by cranking through deductions. And that cranking through the deductions will not land you in trouble. You need a consistency proof. And I should say, in fairness to Hilbert, almost everyone wanted a consistency proof. After the crisis of the Bertrand Russell paradox, people had been going about formulating set theory, the modern guise of set theory, so-called ZFC, which was carefully designed to skirt around any known problems. But you'd want better than that. Really, I wanted a proof that it was consistent. Not just it avoids all known problems, but rather there can be no consistency problems. So everyone wanted a consistency proof. For Hilbert's program, absolutely crucial. It was part of the project. We have to have a consistency proof. And worse for Hilbert, he had to have a consistency proof that, for reasons I won't go into, that was finite. So it was only constructions of finite mathematics, had to prove the consistency of the infinite stuff, but using only finite methods. That was his task. And as you can feel, there's something coming here. There were problems with this. Gödel's first incompleteness theorem from 1931. He showed that there's a sentence in mathematics that's such that if the system is consistent, that sentence is not a theorem, nor is it not a theorem. So what it means is there's a blind spot, if you like. There's a sentence in mathematics that just cannot be derived either way from mathematics. If it's consistent. If it's not consistent, then fine. All bets are off, but that's bad news for another reason, right? So just to give you a sense of what this sentence is like, very, very, unfortunately I can't go into the details for reasons of time, but ingenious way he coded this stuff up. He made a way of coding up every sentence of mathematics and giving the sort of numerical values for all of the propositions of mathematics. Incredibly non-trivial, used for all sorts of reasons all over the place in computing mathematics elsewhere. Very ingenious, often skipped over as, oh yeah, of course you just give a name to everything, but you've got infinitely many of them. You've got to be very careful about how you assign the names. And it's devilishly clever what Gödel did here, but that was just sort of one of the technical language he needed to get this up. But once you've done all that, and here I'll just wave my hands like everyone else, once we've done all that devilishly clever stuff, you've just got a sentence of the form, I am not provable. Okay, now just think about that sentence. And you can, again, think back to the liar paradox, right? Gödel also, you know, philosophers are not alone in kind of worrying about such things. Gödel also worried about the liar, and this is where this came from, thinking about the liar paradox. I am not provable, okay? Think things through here. What if it's provable? Well, then it must be false, because it says it's not provable. So that's an inconsistency in the system. So if you can derive that sentence, if you can prove that sentence, your system's inconsistent. On the other hand, what if it's not provable? Well, then what it says is true. It's clearly true, but not provable. That's the only option left standing here, right? This sentence is true but not provable in the system, if the system is consistent. Again, this makes it, so as I said at the outset, the basic idea of Gödel's is very, very simple. You know, this is the core idea. A lot of details to get this to work, and the Gödel encoding and so on and so forth, but the basic idea is just ingenious. Just, you know, he'd been thinking about the liar paradox far too long. You know, far too long for it to be healthy. Now, this is a problem for Hilbert, right? Because Hilbert thought that you could be able to recapture all of mathematics by playing this formal game, where the formal game is just manipulating symbols via rules. What Gödel showed is that there'll be blind spots. You're going to miss bits. If that's what mathematics is, it's going to miss things. That's bad for Hilbert, but Hilbert might shrug his shoulders and say, yeah, but that's bad for everybody. Okay? Second problem for Hilbert, Gödel's second incompleteness theorem. He showed that no consistent system can prove its own consistency. Modulo a few little caveats here and there, but we won't need to go into the details. No consistent theory with a certain amount of mathematics, a certain amount of arithmetic, can prove its own consistency. This is absolutely devastating blow. Because again, remember what was happening at the time. We've got this crisis in mathematics. Mathematics had been proven to be inconsistent. Shock waves went throughout all of mathematics and anyone who used mathematics. This was devastating. We never want this to happen again, was the sort of the mantra. Working out new theories in ways that would never have these sorts of inconsistencies, but no one was completely confident because they thought that the original theory was fine until Russell came along as well. That looked like everything was hunky-dory there, but it wasn't. So while they were hoping that ZFC, the new theory, was consistent, no one was sure. And what you would really want is a proof that it's consistent. What Gödel showed is, ain't no such animal. There are no consistency proofs, unless it's inconsistent. Then you can have it. But then it's kind of worthless, right? So, basic idea, I won't dwell on this, but the basic idea is, if T is consistent, then G is not derivable in T. So T is just your mathematical theory. If this theory is consistent, then G, which is our Gödel sentence from before, right, the sentence that just says, I'm not derivable, then G is not derivable in T. And you can show, I won't bother with it, it's leave it as a homework exercise if you like, that given the previous incompleteness theorem, if you could have a consistency proof of T, then you'd be able to derive the Gödel sentence. But we've already shown that you cannot derive the Gödel sentence. So you can't have a consistency proof. So the significance of the results, I think, for mathematics alone and logic alone, what do we do about these results of Gödel's? Well, unlike the crisis in the foundations in relation to the inconsistency that had been proven by Russell, that had to be fixed, right? You can't keep going with mathematics when it's inconsistent. I mean, amazingly, a great deal of mathematics, it was business as usual because it was a crisis in set theory. And insofar as you thought the rest of mathematics was just, set theory in sheep's clothing, then, we're in trouble. But that's not to say that you can't continue working in mathematics. Think of crises in other branches of science. You might have a crisis in quantum mechanics, as arguably we do at the moment. Interpretation of quantum mechanics is deeply problematic. Does that mean ecologists should shut up shop until quantum physicists get things sorted out? No. Business as usual in ecology and elsewhere. And so for mathematics, a lot of mathematics went by business as usual, but there were beads of sweat on their brow, I think, fair to say, for 20 or 30 years. Whereas the Gödel results, these are not kind of things that need to be fixed. These are just facts about the systems. This is just a fact about mathematics. It will have blind spots. You cannot derive the consistency of a system that's rich enough to have mathematics in it within the system. You cannot derive every truth of the system. There will be these blind spots. What are you going to do about it? Live with it. That's why it's such a sort of startling result. These are mathematical theorems about mathematics, or as we're often called now, meta-mathematical theorems, about sort of a layer above mathematics. And we just have to come to terms with them. So they're very, very important very, very important implications for all sorts of places, like mathematics and logic, obviously, but also for computing. If you think about what a computer is, well, a computer is a kind of program machine to crank through a bunch of rules, right? What can computers do? Well, insofar as the computer is a instantiation of a Gödel system, there'll be blind spots. Okay, so this led some people to think that, these results aren't just mathematical results now then. They lead to important insights into nature of computation, nature of machine thinking, and you can feel it coming. Is there a difference between human thinking and machine thinking? So let me just run quickly through an argument that has got a lot of press, I think. And perhaps one of the reasons that Gödel's results are as famous as they are is the significance of these results, if any, for understanding the human mind. So Gödel in effect showed that there are blind spots in mathematics, unprovable truths. But the truth of the Gödel sentence, remember the Gödel sentence, this sentence is unprovable, the truth of that's plain to see. Everybody in the room can see that that's true, right? It took us a couple of minutes to think our way through it, but it's clear that that sentence must be true. So there's a true sentence that's not derivable within mathematics. So it's a blind spot by any kind of algorithmic computational system like mathematics or like a machine, but we humans can see it plain as day. It's true. So it looks like, and I'm not endorsing this line of thought, but it's a very natural line of thought. It looks like there's something fundamentally different between the way humans think about these things and the way the machines think. Not surprising, you might suggest, but very, very popular view is that the human brain is just a kind of fancy computer made of, meat instead of silicon. That's all, that it's just a fancy computer. And this line of thought suggests, well, no, it looks like there's something fundamentally different about machine thinking, which has these Gödel blind spots, if you like, whereas the very blind spots that have been demonstrated, at least, are not blind spots at all to a human. So, does this tell us something deep and interesting about the difference between, say, computers and human minds? I don't think so, but it's a fascinating thought, and it's worth sort of dwelling on, thinking about that for a moment. what the Gödel result really shows, and whether that does tell us something different about humans and machines. Why, if I can just say briefly why I don't think it tells us anything terribly important about the differences is, well, on one hand, it's utterly unsurprising that we're not working like a kind of machine that Gödel had in mind, because for a start, we use probabilistic reasoning. We use hunches. We use it's plain to see. I don't need a proof that there are people in this room, despite what various philosophers have said throughout history. I don't need a proof of that. Why? Because I can just see it. I haven't got a proof of that in terms of mathematical proof. It's just plain to see. Okay? And we humans use it's plain to see, probabilistic reasoning, hunches, gut feelings, all sorts of things in our reasoning. And to be quite honest, we don't always distinguish between these different kinds of reasoning. When you're doing something a little bit more rigorous, like in a logic paper, which you rarely carry outside of the logic classroom, when you're doing that sort of reasoning, elsewhere you might, you read an editorial of a newspaper, for instance, there'll be a bit of deductive reasoning, like you might see in a logic class, a bit of probabilistic, a bit of gut feeling, a bit of a whole bunch of stuff, and not distinguished, just all sort of mixed in. So in a way, it's not surprising that humans are not like machines. But that's not what the claim is. The claim is that they can't be. If you tried to model a human mind like this, it just doesn't have the blind spot. So what is it about the human mind? It's almost mysterious, right? There's something mysterious about the human mind that it doesn't have the blind spots the machine has. Well, here's the kind of simple answer, I think. Firstly, it's not surprising because we're a complicated. If we're a computer at all, that lump of meat is a complicated lump of meat, and it does some extraordinary range of things and an extraordinary variety of reasoning that goes on, all mishmashed together. Gödel's result just doesn't apply to such things. So not surprising that it doesn't have the blind spots, at least. But here's a kind of more interesting answer, I think, is that what the Gödel result shows is that on the assumption that the system is consistent, there will be these blind spots. It doesn't say that there are blind spots simpliciter, just that if the system is consistent, there will be blind spots. So when I said to you, but it's plain to see, right? This sentence is unprovable, is plain to see, I said. What I actually smuggled in there with the plain to see was that, and everything you believe is consistent. Your system is consistent. How plausible is that? Not at all, right? We all have inconsistent beliefs about all sorts of things, right? I invite you to sort of think about your own belief systems. And I don't mean in kind of, ways that you should be chastised for. All sorts of, when you're in the logic classroom, you think such and such. When you step outside the logic classroom, you believe something slightly differently. We all have inconsistent beliefs about the city we live in, okay? I know my local neighbourhood, and I have a kind of mental map of that local neighbourhood, and I have a mental map of another neighbourhood nearby. Those maps overlap. Very, very common phenomenon is to think that, such and such a street runs north-south because it's roughly north-south, and then over here I'm thinking about that very same street, but not realising that it's the same street, thinking that it runs more or less east-west, for instance. These very, very common mistakes people make by having local maps of their city and they've got inconsistencies in the overlap of those maps. Utterly implausible that any of us have consistent beliefs. In fact, if you do, come and talk to me later because you deserve a medal. You really do. So what I did when I said it's plain to see was actually smuggle in a really, really heavy duty and false assumption that the system is consistent. Okay, that's just utterly implausible. And indeed, it's implausible for very good reasons for which Gödel pointed out to us. You cannot prove the consistency of the system. So in effect, what I've done is not just smuggle in the consistency of the system, but it's known to you that the system is consistent. You know no such thing. Gödel's second incompleteness theorem, in a way, ensures that that can't be the case. Still, it's an interesting thought, isn't it? There is this fundamental difference between minds and machines. I'll finish off now with just leaving the incompleteness stuff aside And I just want to say a couple of things about one of the lesser known results of Gödel, but I think it's one of my favourites. I just think it shows how quirky the guy was. So this is Gödel and Einstein, regular walking partners at Princeton in the 1950s. And no doubt over various conversations with Einstein, Gödel came up to speed. He was a smart guy, right? He didn't really work in mathematical physics, but he was a smart guy. And he came up to speed on general relativity. Came up to speed, actually a little bit more than up to speed. Came up to speed to the point where he could publish in the area. And published a startling result. So he found that there's this really odd model of Einstein's equations. So Einstein's equations are the equations that describe the way space-time is, or the way it could be. The details are going to depend on the distribution of matter and the like, but these are the big global constraints, if you like, how space-time is structured. And what Gödel showed was that there were these really odd solutions that no one could have been looking for, because they were looking for solutions, for the most part, that looked something like the universe we live in. And what Gödel found were these really kind of odd solutions, but basically a big rotating disk, a universe that's a big rotating disk. And he found that in such a universe, there were closed time-like world lines. Okay, what that means is a world line is just a sort of a trajectory of a particle through space-time. Okay, closed means it comes back on itself, right? World lines, you know, if you think about my world line, it sort of started in some place, I moved around in space, and as time went by, I moved. So I've got this kind of trajectory. What a closed time-like world line looks like is a world line that comes back on itself in the temporal dimension. In a word, time travel. It's a kind of time travel. If space-time has the right kind of structure, and you're cunning enough to sort of shoot a rocket in the right sort of direction, you can come back on yourself at an earlier time. You know, just for a moment, just sort of think about the kind of mind that, you know, he's working in mathematical logic, and just over a conversation with Einstein comes up to speed on general relativity and thinks, what about the big giant rotating disk with world lines that come back on themselves? Extraordinary sort of chain of thought. Why is this interesting? Well, it's very important philosophically, because various arguments people have put forward to suggest that time travel is logically impossible. You often hear that said in philosophical circles. There are logical paradoxes if you have time travel. You go back and kill yourself as a baby, for instance, before you got old enough to build a time machine to do the going back and doing the killing, and you've got this paradox then, did you do the killing or did you not? So-called grandfather paradox. It usually involves slaughtering a grandfather, but you can make the circle tighter by just doing it to yourself. Auto-infanticide is the technical term in philosophy. And that's supposed to show, according to some, that time travel is logically impossible. It gives rise to a logical paradox. Well, what about Gödel's solution to the Einstein equations? He's shown that it's actually consistent with our best physical theory, consistent with general relativity, that there are closed time-like world lines. These are not just logical possibilities, these are physical possibilities. That's much stronger. So, not to say that we do live in such a universe, the claim was never that, just that it's certainly physically possible that we could live in such a universe. It's consistent with Einstein's theory, and if we did live in such a universe, there would be these trajectories. So it puts pressure on those who think that time travel is logically impossible. You still might defend that view and say what's going wrong in the Gödel cases, but very, very interesting line of thought of Gödel's. And I think I might leave it there. That's a good place to finish. I really just wanted to mostly focus on the incompleteness results, which are what he's deservedly famous for. And not famous enough in my books, but, you know, of course I would say that. But this last little bit is just to give you an idea of sort of the quirkiness and the broad-ranging interests he had, you know, to actually think about this in 1950s, be on top of general relativity enough to publish in respected physics journals. You know, most physicists would be pretty pleased to be able to do that. And here's someone who's dabbling, really. He's a mathematical logician. This is way away from his normal work, and he's up to speed on general relativity. Not just up to speed on it, as I said, but up to speed enough to see really quirky and weird results that had bypassed everybody else. So I'll leave it there. Thank you.